This lab investigated the physics laws behind the motion of a free-falling object. The rules that govern free-falling motion on Earth can be seen when analyzing the relationships between an object's position, velocity, and acceleration over time, and the forces that act on the object to produce this motion. To create a visual for this investigation, a video of a pillow drop from a high initial position was used. Let's talk about what we know about free-falling objects. On Earth, the force that acts constantly on all objects is gravity. The gravitational force on an object is composed of the mass of the object times g, which is the gravitational constant on Earth, a value of 9.8 meters per second squared. Thus, the gravitational force on an object with a larger mass will be larger. On Earth, there is also drag force, or air resistance, acting on a falling object. Both of these are impacting the pillow's motion as it falls. The video was analyzed in Tracker, and the position versus time data for the y component of motion was transferred to an Excel spreadsheet and plotted to be compared with our model data. When formulating the model, we know to determine the change in position of a free-falling object, we need the velocity of the object and the time. To determine the velocity of an object, we know that this value will be dependent on the forces acting on the object, from Newton's second law. We will use the equation final velocity equals initial velocity plus F net over m times delta t to determine the velocity of the pillow over time increment t equals 0.33, and from there we can determine the position of the pillow. To determine F net, as shown here, we illustrate the scenario with a diagram. We can then calculate that the net force, or the total amount of force on the pillow, is equal to the gravitational force plus the drag force. Then we can compute the net force, neglecting the impact of drag, as shown here. Using our code in VPython to represent these relationships as equations, we can calculate the model position data. However, because the motion of the pillow was only captured over a small window of time, we see that there is a disparity between the observed motion and computed motion. The computational model shows a more accurate representation of motion approaching terminal velocity, as we can see that the slope of the position graph is decreasing at an increasing rate. Once the velocity can no longer change at a larger rate, the slope will be vertical on the graph, which represents terminal velocity. Terminal velocity occurs when the velocity of the object and the acceleration from the Earth's gravitational force are equal. Shown here are the computational models with and without drag force. The data points are essentially the same, which leads us to conclude that this model is not very accurate for the motion observed in this experiment. If the pillow is thrown with initial velocity in the negative direction, it would take less time for the object to reach terminal velocity. However, the value of terminal velocity would be the same. As we can see in the model, if we adjust the velocity, the position change occurs more rapidly, but has the same trend in motion. The model with drag, shown here, has a final position of negative 4.75 meters. This demonstrates how a greater initial velocity will impact the drag force, and thus the change in position of the pillow. Neither of these models reveal terminal velocity, as this motion is over such a short time interval.